Good morning, class, and good afternoon to the 8th period class. This is Mr. Weldon. We're going to be talking about a couple of gas laws today. We're going to be talking about gas pressure in a closed container and what causes it. And we're going to be relating several different things from earlier classes, specifically kinetic theory of matter, when we're talking about pressure. Now, I know I'm not there and I can't draw on the board some of these concepts, but I'm pretty sure if you follow along with me, you'll get it just fine. There's a couple of math examples we're going to be working on today, and some math practice problems that go with it. We're going to be applying algebra concepts that you've learned before, but I don't think it's anything that you can't handle. It's multiplying and dividing, and that's pretty much it. We're not going to be having to take any square roots of anything. I think you got this. So let's move on. First, we have to know what pressure is and what we can do to affect pressure. If you've ever pressed against someone's skin with your finger, then you can feel the pressure. They can feel the pressure pushing in. And the harder you push with your finger, then you're getting a greater force. Think of it like this. If you walk into a wall head first, you're gonna feel some pressure on your noggin. If you run into the wall, you're gonna feel a lot more pressure. You're gonna feel a greater force. The faster something moves, the greater force you're gonna get. Well, what causes things to move fast? What causes this greater force? Well, you want them to move fast. How do you get something to move fast? How do you get these particles to move fast? Going back to kinetic theory of matter. If we need to convert something into kinetic energy, what do we need to give it? We need to give it thermal energy. Thermal energy gets converted into kinetic, and then it moves at a greater pace, causing greater pressure. Also, if we lessen the area or the volume, that can also mean greater pressure. Think of it like this. Imagine you held up your hand and someone put a small wooden block on your hand and then put their hand over the wooden block and push just a little bit. Well, you would feel some pressure, but it wouldn't hurt. It's not going to really do anything to your skin. Now imagine they took a thumbtack and they put it over your hand and then put their hand on top of the thumbtack and press with the same amount of force. Well, you would feel a lot more pressure, so much pressure, it would probably pierce the skin. It would probably hurt a lot because that's a lot more pressure. What causes it in a closed container are collisions between the gas particles and the walls of the container. Think of it like this. You blow up a balloon, you're putting in the gas particles. Remember that the kinetic theory of matter says that the gas particles are constantly moving, they're constantly bouncing back and forth. They're hitting each other, they're hitting the walls of the container. Remember, if you blow up a balloon, well, when you started, the balloon was deflated. It was all shrunken. It wants to get back to that part. It wants to get back to being deflated. But the gas particles bouncing off each other are keeping that from happening. It's a lot of force there. I think that's pretty amazing that you can't really see it, but it's strong enough. All these particles are moving so fast and with so much force, they're keeping the rubber balloon from collapsing in on itself. One of the things that can affect pressure is temperature. If we raise the temperature, it raises the pressure, but of course only if the volume and the number of the particles are the same. So remember kinetic theory of matter. We give it more thermal energy, it raises the temperature, that gets converted into kinetic energy, and the particles move faster. And if they're moving faster, they're going to be hitting the walls more often. Think of it like this. Let's say we put someone in a box. We put them in the middle of the box and they start moving. And they move at a random rate or a random direction. They're moving at, let's say, 2 miles an hour. Not very fast, a very slow walk. They hit a wall, they turn around, and they keep moving. Well, they're going to be hitting the walls, but not that fast. If we get them to move a lot faster, we say we give them some coffee or something, some Mountain Dew, they're going to be bouncing off the walls more often. That is what causes the pressure. We are used to working with the Celsius scale, and a lot of science-y things, probably something you learned in middle school, that science uses the Celsius scale where water freezes at 0 and boils at 100. But the problem with the Celsius scale is it has a negative temperature. You can go to like negative 40 degrees Celsius or negative 200 degrees Celsius. But the problem with a negative scale is when we're talking about certain math equations. If we put in a negative number, it's not going to turn out right. So we're going to be using the Kelvin scale. The Kelvin scale starts at 0, doesn't have any negatives, and just keeps going up. The way you want to convert it is add the number 273 to a Celsius number. So if it says, let's say 30 degrees Celsius, let's say 30 degrees C, add 273. Remember this, if you see a C, add 273. Volume also affects the pressure. Think of it like this. Let's say you had a balloon, you blow up just a little bit, and you tie it off, but it's not blown up that much. You put in just like a half a breath. It's still wrinkly on parts of the balloon, and it doesn't bounce. Well, if you squeeze the balloon a little bit, you put it between your hands and you give it a good little push, parts of the balloon will stick out a little bit, and it'll feel like an inflated balloon, partly. And that's because you've increased the pressure. These gas particles that are inside the balloon, you've essentially cut them off, you've closed in the walls together, so now the particles don't have to go that far. Let's take that person in the box example I said earlier. So they're bouncing around, they're going at that same rate. Well, if you cut the room in half and build a wall there, well, they don't have as far to go. They'll still be bouncing off the walls at the same slow pace, but they don't have to go as far. They're able to hit the wall more often, keeping it from collapsing in on itself. That increases the pressure. Let's say instead of one person in a box, we put 100 people in the box. Well, they will certainly be hitting the walls more often. Remember, hitting the walls more often increases the pressure. So if we put in a lot more particles, if we blow a balloon up more, we put more air into the balloon, that's going to increase the pressure. And you know what happens if you put too much gas particles in a balloon. The pressure increases so much that it's gonna pop. That happens with pretty much anything else as well. If we decrease the volume so much, let's say we squeeze the balloon too much, well, what's gonna happen? We increase the pressure so much and it can pop. If you put air in a jar, let's say we seal it tight, you heat it up, it can also cause it to burst. Let's take a look at Charles's law. Charles's law says that volume and temperature are directly proportional, which means, let's say we increase the temperature, it's going to increase the volume as well. Let's say you had a pot of water on the stove, and you give it some heat. Well, those particles are going to start moving. Remember that eventually they're going to change phases. Well, they're going to take up more room. Steam takes up more room. Even if we convert it to a gas, once we give it even more temperature or we give it more heat, it's going to take up even more volume. It tries to spread out even further, because remember, we're taking that thermal energy, we're converting it into kinetic energy, and by doing that, we're getting them to move a lot faster. And if they're moving a lot faster, they're spreading out. And if we reduce the temperature, you're going to be reducing the volume. We're going to be seeing a very cool video, I think a really, really cool video, at the end of the slideshow to help. It's not in the slideshow, but the words are in there. So get the substitute to highlight it, copy it, put it into Google Chrome, paste and watch it. It's about a few minutes long. I think it really demonstrates Charles's law pretty well. So if you, anytime we're working with the problems, if you see a problem and it has volume and temperature in it, then you know you're going to be working with this formula. All you have to do, it'll give you 3 numbers, and it'll ask you for one of the remaining numbers. Put the numbers in, solve on one side, and then figure the rest out. It's something that I'm sure you'll be able to do. These are, it's a simple algebra technique. So let's say we had 600 milliliters of air, and 600 milliliters is volume, so we're working with a V, and it's at 20 degrees Celsius. What's the volume at 60 degrees Celsius? Remember, we see a C, so what do we need to do? We need to add 273. We got to get it out of Celsius. We need to add the 273 to put it into Kelvin. So we add the 273 to 20, and we get 293. I'm going to work on this on my calculator as well, so we can work on that. I'm going to go right back. You can see, write down that formula, V1 over T1. So that's V1 divided by T1 equals V2 divided by T2. So we do V1, which is 600, divided by T1, 273 plus 20 is 293. So 600 divided by 293, what do we get? And we get about 2.05. And that's going to equal whatever the volume is. That's what we're looking for. V2 divided by not 60. We got to remember, we got to convert it. What's 273 plus 60? It's 333. Yes? To make sure, 273 plus 60 gives us 333. So we have V2 over 333 equals 2.04. Well, how do we get the V2 all by itself? Well, we just need to multiply both sides by 333. So we'll take the 2.04 times 333. We get what now? Should be 679. I think the next one is a lot easier. Boyle's law. Boyle's law is a lot easier, I find, because it's just multiplying and then you're going to be dividing by whatever the other number is. It says that the pressure is inversely proportional to the volume. That means if you increase the pressure, the volume goes down. If you squeeze the balloon, you increase the pressure in the balloon, you're squeezing the volume tighter and tighter and tighter. And that's going to be equal to P2 V2. P1 V1 equals P2 V2. This type of formula pops up all over the place in chemistry. Go ahead and write down that formula, because we're going to be working on the next problem, and it's going to be dealing with Boyle's law. So let's say a gas occupies 12.3 liters at a pressure of 40 mmHg. mmHg stands for millimeters of mercury. It's a type of pressure measurement. You can either measure pressure at mmHg or ATM. ATM stands for atmospheres. Right now, you're in about 1 atmosphere of pressure. If we were to double the amount of air sitting on top of you, that would be 2 atmospheres, kind of like that. So let's say gas occupies 12.3 liters, that's a volume, at a pressure of 40 mmHg. What's the volume when the pressure is increased to 60 mmHg? So it's P1 times V1. So we got the P, which is 40, put that in my calculator, times the volume, which is 12.3. What do we get? We get 492. So 492 is going to equal P2 times V2. Well, the P2 is 60, so it's 60 times V2 equals 492. Well, how do we get the V2 all by itself? We just need to divide both sides by 60. So 60 divided by 60 is the 1 times V2 is V2, and then so we just need to do 492 divided by 60. Put that in your calculator. What do we get? We get 8.2. Don't forget to use units. Sorry, I don't know where I went there for a second. Don't forget to use units. That would be 8.2 liters. This is the YouTube video I want you to watch. It's a few minutes long. It shows Charles's Law in action. And you're going to be shrinking a balloon, a fully inflated balloon, shrinking down. And remember to watch the whole thing. The teacher may want to exit out. I'm going to have the link on the email I sent Miss Neal and the substitute this morning. Then they'll be able to play that for you. After that, work on, it's a two-sided sheet that has you work on Charles's Law and Boyles's Law. Now, they don't say which one is Charles's Law and Boyles's Law, but if you figure it out, if one's talking about pressure and volume, you know you're going to be talking about Boyle's Law. If it says volume and temperature, you're going to be working with Charles's Law. So figure that part out. So work on those. After you finish that, then I want you to work on a crossword puzzle. It's a vocabulary crossword puzzle for the things that we've been working on for the past few weeks or so since the semester began. And if you still have time left on the clock, open up the textbooks to sections 3.2. It's talking about gas laws, and answer the questions at the end. If you need anything, I'll be there on Wednesday to see you guys. Have a good one.